All right, welcome back, everyone. Today I'm going to discuss the early experiments that led to the subatomic structure of the atom, and then we'll discuss the isotopic notation that's used to describe different isotopes of atoms, and I'll introduce ions, and we'll learn how to name some elementary compounds. To start off with, the first major experiment into the actual substructure of the atom began in 1897 with J.J. Thomson's experiments using electrode cathode rays. And what he was doing was taking these evacuated tubes, meaning they had pumped a vacuum and removed as much air out of it as they could, and passed electricity through the cathode that was on one end of the tube. And they noticed that when they did this, there was a glow that emanated from the cathodes, and so they called these cathode rays. Now, the cathode was the negative side of the tube, and so these rays that were emanating from the negative side were deduced to be negatively charged particles. And this was a different type of light than typical light because it could be deflected by magnetic and electric fields, and it was shown to have mass. So this was really important in the early investigation of the atom because now we know that there's these particles that are much, much smaller than atoms, and they're negatively charged. At the time, J.J. Thomson called these corpuscles, but now they're called electrons. And Thomson started to put this into a theory, and this plum pudding model can be shown to the right, where it was known that atoms had a positive charge, but it was thought that that positive charge was diffuse across the entire atom, and that there was an unknown amount of these corpuscles or electrons that were spread throughout this sea of positive charge. This was an early experiment, but nonetheless it was very valuable, and some of this work led on to further discoveries. And so the next major discovery to be made was that of the nucleus of the atom, this small region at the center of every atom that contains most of the mass of the atom. So inside of this nucleus are the protons and the neutrons. Now, when Rutherford, or Ernest Rutherford, was doing his experiments in England, he had a source of radium, which was a radioactive source, and it emitted these particles that were different than the corpuscles of Thomson. They were positively charged particles that had a mass similar to helium. So they had 2 protons and 2 neutrons. At the time, we didn't know what protons and neutrons were. And Rutherford had set up an experiment where they took a thin sheet of gold. So let me zoom in on here. They had a thin sheet of gold metal, and they took this radium source of alpha particles, and they passed it through a slit to get a small beam of alpha particles, and they ran an experiment where they had a screen that was made out of a phosphor, similar to the one here, and that would grow green whenever there was a particle that hit it. And so most of the particles, they deflected, so they were undeflected, and they went right through the sheet of metal. And maybe some of them deflected slightly. And this was to be expected because most of those particles were thought to be very small, and the gold particles were thought to be very big. And if the inside of that gold atom was a diffuse positive charge, if something were to come near it, it might get deflected. Now, there was these particles that were deflected a much greater amount, right? So they were even bounced backwards. And Rutherford had said at the time that it was like if you shot a cannonball at a sheet of tissue paper and then it bounced back at you, that was as if that was the type of results that they were discovering at the time. And the only way that the theory would work with this large deflection was that the nucleus must be very, very small, and that it's very, very dense. And so the center of the atom was occasionally a particle would get near it, and if it did, then it would get deflected back this way. But most of the time, they pass just right through because most of the atom is empty space. Okay, so with the discovery of the nucleus, we kind of assumed that the nucleus is where the positive charge was, but it wasn't until a further experiment by Rutherford where he bombarded nitrogen gas with alpha particles that he observed that there was a small particle that was being emitted. And this was a hydrogen nuclei, a H1 element, H1 atom. And this hydrogen nuclei corresponded to approximately 1 AMU, which was the lightest, simplest component at the time that we know of all atoms, and it had a positive charge that was equal in magnitude and opposite in charge to that of the electron. Now, there was other experiments along the way that discovered the mass and the charge of the electron. I didn't mention them here, but they're very important to know about as well if you are interested in the history of chemistry. And then it wasn't until 1932 that a student of J.J. Thomson, I believe, Chadwick, did some experiments similar to Rutherford, where he bombarded beryllium with alpha particles, and this was a common theme at the time. They were just kind of shooting different elements with an array of alpha particles and trying to see what they discovered. And in this time, they discovered a particle that was similar in mass to a proton, but it didn't have any charge to it. And that's part of the reason the neutron went undiscovered for so long. And it helped tremendously solve some of the problems of chemistry at the time, because we knew that there was something that was adding mass to the atom without changing its identity. And neutrons are the key to understanding that. So let's look at the summary of the subatomic particles. The first particle that was discovered was the electron. Its mass was found to be 9.109 times 10 to the negative 31 kilograms. And in terms of AMUs, that's about 1,836th of an AMU. So it's a very small mass, indeed. It's got a charge, though, of -1 elementary charges. An elementary charge has this number of coulombs. It's a small charge corresponding to a coulomb. And it's located outside of the nucleus. So it can be found in the nucleus under very, very rare situations. But most of the time, we're going to think about the electron as being outside of the nucleus. And it's going to exist in these shells we'll talk about. Now, they're not exactly circular, but we'll get to there. Now, the proton and the neutron are particles that exist within the nucleus. And they are approximately the same mass. However, the neutron is slightly heavier, so we can see that here. And the proton is equal in magnitude, but opposite in sign to the charge of the electron, and the neutron has no charge. And here's that conversion between AMUs in kilograms. And so we can derive this later on through the mole we'll talk about later on. All right, so let's kind of draw ourselves a little picture here. So a lot of times we'll see the diagram of the atom drawn like this. And we'll say, okay, yeah, we have our nucleus here, and inside the nucleus are the protons and the neutrons, and then on the outside are the electrons. And the electrons are much smaller than the protons and neutrons, and they kind of orbit this nucleus in a way, kind of like planets orbit the sun. We'll learn why this isn't quite correct, but that's kind of that standard diagram you've seen. Now, I do kind of want to bring up a little bit more about why a proton and a neutron have the charges that they do. So I mentioned in the last lesson that protons and neutrons are made up of elementary particles called quarks. Now, a quark is the smallest component of baryonic material. There's two first-generation quarks, the up and the down. And the up quark is given the symbol U, and down quark is given the symbol D. And each of these quarks has an elementary charge. And the up quark has a 2/3 elementary charge, and the down quark has a negative 1/3 elementary charge. So if we're going to draw a little bit more of a specific picture of the proton and the neutron, we can do that. So every proton is made up of 3 quarks, and every neutron is made up of 3 quarks. But the proton is made up of 1 up quark, 2 up quarks and 1 down quark. And each of these quarks has a color component. And they're held together by gluons. Those are those strong forces that are holding together these quarks together. And this would be 1 proton. Okay. And then for the neutron, we have the same kind of deal here. So we're going to do our up. But now in this case, we're going to have 2 down quarks and 1 up quark. Let me draw my circles here. Doesn't matter. They're up and down quarks. They're not able to actually be measured how big they are. So drawing them as spheres is kind of what's the word? Misleading in some sense. But anyways, so the size of a proton is roughly on the order of 1 × 10⁻15 femtometers. Neutron's about the same. A little bit smaller than that. And the size of an atom is approximately 1 × 10⁻10 meters. Oh, sorry, I shouldn't say. I should write this as meters, I'm sorry. So this is about 1 femtometer, 10⁻15 meters. And this is approximately 1 angstrom. So there's an order difference about an order of 10 to the 5th difference between the size of that nucleus and the size of the atom. So the nucleus is really, really small. And now, how do we get the charges here? Well, if we have 2 up quarks, an up quark is a 2/3 positive charge, and a down quark is a negative 1/3 positive charge. So 2 times 2/3 is 4/3 minus. Oh, wait a second. All quarks have a positive charge. I'm sorry about that. Oh wait, no, that's right. So we have to add them together. So adding a negative. So 2 times 2/3 is 4/3, and then we add a negative third, and that gives us a positive 1 electric charge for a proton. And then a neutron is 1 times 2/3 plus 2 times negative 1/3. and that's going to cancel out, and it gives us a 0 electric charge. Okay, so the proton and neutron, they're very similar, but they have different charges because of the differing number of up and down quarks. Okay, so that's an interesting thing. If we go on to learn about nuclear chemistry, we'll see that up and down quarks can be converted. And what we can say here is that the proton, which I use the symbol P+, and the neutron and 0 is what I use, these are composite particles. They're made up of quarks. And the electron is an elementary particle. Quarks are also elementary particles. All right, so let's talk about isotopes. There's this really interesting table here. I have it linked on our page, and it gives the atomic weights and isotopic compositions for all of the known elements. I don't know if it has the synthetics as well. It has some of them. It's my cat. She's trying to get outside. It's nice out right now. Okay, so we can take a look here, and we can see the atomic masses of the different elements, and we'll see that some of the elements have more than one number listed. These are the isotopes of the elements. So I have, for example, carbon 12, carbon 13, and carbon 14. The only difference between these three isotopes of carbon is how many neutrons that they have. So let's talk about this. So previously, scientists arranged the elements by their atomic weight, which is also known as the atomic mass. Weight and mass are typically used interchangeably in chemistry, but weight refers to a force on a material, whereas the mass is just a property of that material. So it's more proper to use mass. And then, but scientists, they realize that some elements with less protons are actually heavier. We talked about that with cobalt and nickel. Now, Chadwick, his discovery of the neutron helped us understand Francis Aston's works, where he realized that some elements can have a different atomic mass with the same number of protons, and that was the neutrons. So a lot of times in chemistry and in any science, there's going to be this discovery that someone makes by theory, but they don't go on until later to actually find that mystery particle. All right, so let's look at isotopic or nuclide notation. So in the middle, what we'll do is we're going to list the symbol. Okay, so the atomic symbol, let's say it's X. There's no atom with that symbol X. And then in the bottom left corner, we'll write the atomic number, which is the number of protons, or more correctly, the charge on the nucleus. And then the top left number, we'll write the mass number, which is not the atomic mass. It's just the sum of the number of protons and neutrons. And then in the top right, we can write the charge on that nuclide. Okay, whether it's neutral, whether it's positive or negative. And let's look at a couple different examples here. The first and simplest isotope is hydrogen 1. So hydrogen 1 has the notation like this, and this would be a neutral element. So we can write it like this, hydrogen -1, or we can write the symbol like this. Sometimes we leave out the atomic number because the atomic number is should always be the same as the symbol that's given. So a 1 down here means there's one proton. And when we have one proton, we have we have hydrogen, right? So this hydrogen 1 nuclide has, let's kind of write it out like this. It's got 1 proton. It's got 0 neutrons, because the sum of the two has to equal this top left number. And how many electrons does it have? Well, every neutral atom has the same number of electrons that it does protons. So in this case, it has 1 electron, because the sum of them have to equal the charge. Now, the next simplest nuclide would be hydrogen 2. So hydrogen 2 would have 1 proton and 1 neutron. And hydrogen 2 is given a unique name. It's one of very few nuclides that has its own name. It's known as deuterium, or heavy hydrogen. And it's given the symbol D, so you'll see that as well. It's the same. 1 proton, 1 neutron, and 1 electron. And then if we keep building this up, we can add 1 more neutron onto hydrogen before it becomes, and at this point it becomes unstable. So if you add another neutron here, it becomes kind of neutron heavy. So this is known as tritium, which has a half-life. It starts to decay after a certain number of years. I believe it's around 12 years for tritium. So we can write H31 or T31. And tritium has 1 proton, 2 neutrons, and 1 electron. If we start to add another neutron onto hydrogen, it decays very quickly. Now, some people have discovered hydrogen 4, but it's not going to be listed in this table. Now, each of these isotopes has its own mass. And what we can do is we can think about what the abundance of each of these isotopes that makes up a sample of average hydrogen is. And most hydrogen, 99.99% of it, is going to be H1. And then 0.0001% of it is going to be deuterium, and then trace amounts of tritium will be present. So you can actually calculate the standard atomic weight of that sample of hydrogen by taking the atomic masses multiplied by their isotopic compositions and then adding them together. Now, hydrogen is not a great example of this because it tends to vary. Which is kind of interesting and does that. Let's look at another example that doesn't vary. A good one of that is element 35, which is bromine. So let's look at bromine. Well, it does vary a little bit, but very small. So let's look at bromine. I like this one. So bromine is element 35. It's in the 17th group of the periodic table. And oftentimes in this class, you're going to want this periodic table next to you. So bromine is over here. And the small number here is the number of protons. And then this is the average average atomic weight of all the isotopes that make up bromine. And when we look at this, this number is really close to 80. Okay, and I use this example because it can be a little bit misleading. You might think that the most common isotope of bromine is bromine 80. But it's not. So let's take a look at that. So there's 2 common isotopes of bromine. There's bromine 79 and there's bromine 81. All right, so bromine 79 has 35 protons. And then how many neutrons does it have? Well, it's got 79 minus 35, which would be 44 neutrons. And then for the neutral bromine, it's going to have 35 electrons. All right, so for bromine 81, this one's going to have the same number of protons. That determines its identity. the number of neutrons here now is 46. And it's going to have 35 electrons as well. Now, what is its standard atomic weight for all a bromine sample? Well, we need to know a couple things. We need to know what the atomic weight of bromine 79 is, and we need to know what its abundance is. That's where this table comes into handy. So we can pull that information here. I'm just going to take a couple sig figs. I'll just kind of do it like this. Okay. Come on. All right, so what I'll write here is this is the isotopic weight. Oops, I spelled that wrong. And we're going to do this in terms of AMUs, okay, instead of kilograms. So the isotopic weight of bromine 79 is 78.918 AMUs. For bromine 81, it's 80.916 AMUs. And then its percent abundance is going to be this column here. So it's actually not a, it's a fractional abundance. Fractional abundance is 0.5069, and this one is 0.4931. And what we can do is we can multiply these together, and then we can add them together to get what the average atomic weight is. Pull my trusty calculator. Okay, so 40, and the other one is 39.899, and then we can add them together. And we'll get 79.8996, or just round it to 79.90. So this is the standard or average atomic weight or mass for bromine. So you have to do this for all of the major isotopes for a specific element, and generally that ranges from 1 for things like arsenic, there's only one main isotope, to 2 to, well, here we got 6. Some of them have quite a few, but it never usually more than like 7. So we'll have like a range, and it's interesting to look at some of the different main isotopes that are found in nature, and just to kind of pay attention to that when you're learning chemistry for the first time. Okay, so that's a little bit about isotopes and about how to find the average atomic abundance, or average average atomic mass of a element. Let's clean this up just a little bit. Okay. Now let's discuss ions. And an ion is whenever a neutral atom loses or gains an electron. So when a atom loses an electron, it now has a larger positive charge because some of that neutral, some of those electrons are gone now, and electrons have a negative charge. So you got to kind of think in opposites. So something loses an electron, it's losing a negative charge. So overall, that atom becomes more positive. And the opposite is the case when it gains an electron. right, so we lose an electron. We form a cation. All right, so a cation is a positively, there's my cat there right on cue, charged atom. That's right, I'm talking about you. Okay, so we have positively charged cation, and we have too few electrons, and to neutralize the number of protons. An example of this could be pretty much any metal. So if we have a gold atom, gold can lose an electron, and we can write it like this, where we'll have, why did it do that? Okay. It can lose an electron, and when it does, it becomes positively charged. And this is how you write an ionization equation. All right, when an atom gains an electron, it becomes an anion. This is a negatively charged atom. All right, so an example of this could be any halogen, like chlorine. Chlorine can gain an electron, can capture one, become negatively charged. So now it has too many electrons, and the number of protons cannot neutralize it. All right, so anytime we gain an electron, it goes on the left side. We can also have a series of electrons being absorbed by an atom. So we can think about, let's take a look at our periodic table. Okay, like sulfur, for example. What about sulfur? Well, sulfur is to the right on the periodic table, and we're going to soon learn that anything that's to the right of this kind of zigzag line, this kind of staircase, is going to typically want to gain an electron. Anything that's to the left of it will typically want to lose an electron. And we'll explain why that is later on. And then this column here, this 18th column, this typically doesn't like to neither gain or lose an electron. All right, so sulfur, because it's to the right of the staircase, will want to gain some electrons. And when it does this, it will typically gain 2 of them, so that it has the same number of electrons as this argon molecule over here. And so, say for example, sulfur, we're going to have sulfur plus an electron, and then it becomes sulfur minus. And then that sulfur minus ion can capture another electron to become sulfur 2 minus. Okay, so a doubly charged ion. There's a term that is used throughout your book a lot, and it's called isoelectronic. So an isoelectronic ion has the same number of electrons as another ion. So that's just a term for saying same number of electrons. So let's look at a couple of examples of isoelectronic ions. We have magnesium 2+. So magnesium 2+ would have 12 electrons minus 2, because it's lost 2 electrons. That's why there's a 2+ charge. So magnesium 2+ has 10 electrons. What's something else that has 10 electrons? What about sodium that's lost 1 electron? Okay, so sodium plus, that one also has 10 electrons. We could also think about, on the other end, neon. Neon has, if it's neutral, has 10 electrons. And then fluorine minus, if it gains an electron, it would have 10. And then oxygen 2 minus, if it gains 2 electrons, has 10 as well. All right. So we're doing pretty good. We've learned about isotopic notation, the atom, and the last topic I'm going to cover in this lesson is on naming compounds, like simple compounds. And if we're trying to name compounds, we want to do it systematically in chemistry so that we don't confuse our audience, right? So we want to make sure that we're using the same language. So the best way to do this is to use a series of rules, and we'll start with we'll start with some compounds that contain metals and nonmetals, okay? And then we'll talk about compounds that have 2 nonmetals. And because these will have differing set of rules that we need to learn, and I'm going to kind of introduce this slowly throughout the class so that we can get a handle on it. So anytime we have a metal and a nonmetal, we're going to refer to these as ionic compounds for a reason that we'll learn later on. They have a type of bond that's unequal in its sharing. So these are ionic compounds. And we'll talk about fixed charge metals first. So these are any metals that are found in the first or second group of the periodic table. And the groups are the columns, so up and down, vertical columns. So and hydrogen here is not a metal. So hydrogen is a nonmetal. It's above this metal-nonmetal dividing line. So what we're referring to here are any compounds that are made up of lithium through francium, beryllium through radium, and then there are some other metals that are fixed charge in this transition metal block, but there's not too many that are fixed charge. Some of them are silver and zinc. And I'm trying to think of a couple more, maybe scandium and yttrium. And then there's a couple other metals that are worth noting. Aluminum, it is a fixed charge as well. Maybe gallium as well too. Now, if we just kind of talk about these couple metals to begin with, because there's so many elements to talk about. All of these form compounds with groups over here, like nitrogen, oxygen, and fluorine. And so these non-metals, these are things that are to the right of this staircase, are really easy to name. All right, so that's why we're starting here. Now, the main assumption here is that anytime we form one of these compounds are going to be electrically neutral, meaning we need to have one of these metals being positively charged and one of these nonmetals being negatively charged coming together to cancel each other out. We'll talk more about this later on. And we can find the most common charges of ions through another table here, and I'll make sure it's on our modules so we can find it easily. And I'm still working on our page here, so it's going to look a little different. But there is this periodic table chart. Periodic chart of the ions. This one is really helpful. It breaks down all of the ions and includes the polyatomic ions that we'll learn later on for all the elements. And so it's really helpful for seeing what the most common charges are. All right, so we'll take a look at this later on. We'll notice some of them are uncharged as well. But let's start with some basic definitions. So what we'll do is we'll take a metal and the metal is always going to be listed first. And then to name it, we'll look at what the non-metal is, what its name is, and we'll change the ending to IDE. So we'll have the most common name of the non-metal, and then we'll just change the ending to IDE. So if I form a compound that's made of sodium and chlorine, we'll name it as sodium chloride. So there's going to be a space, and all of these are going to be lowercase names. So the names of chemical compounds are not proper nouns unless they're used in like a title, or you're like listing this as the first word in a sentence, then you could capitalize it. But typically it's non-capitalized. Another example of this, so it wouldn't be sodium chlorine, by the way. So we have to change it to IDE. So it's kind of like listed as like that. And then here's a couple other ones. Let's look at this chart here. I have yttrium. Okay, yttrium is a 3+ charge. Let's just use something more simple. So strontium here. Okay, so if I look up strontium chloride, we'll see it's listed as SrCl2. Strontium chloride. And we just name it like that. Okay. Now, why is there 2 chlorines here? Well, it needs to be electrically neutral, and we can see here strontium is a 2+ charge, and chlorine is typically a -1 charge. So we have a 2+, and we have 2 1- charges. Those cancel out to be electrically neutral. All right, we can do a couple more. These are fairly straightforward. Let's say we have beryllium oxide. So beryllium oxide is BeO. The hardest thing is spelling this one right. BY. I think that's right. I have to look it up. No, it is BE. Okay, and the reason why it's BeO is because it's 1 beryllium is a 2+ charge, and 1 oxygen is typically a 2- charge. We can see that right here. And we can also look at the names here. So this is beryllium oxide, so we can just look at the names on this chart, which is different than it is on this chart, right? So this is another sweet way to do this. Okay, so okay. So you can practice this, and I'll have some problems in the homework set for you to do on this. All right, now anytime we have a non-metal and another non-metal, these are different types of compounds. They're specifically called molecules. They're covalent molecules because the bonds that are shared between the atoms in a molecule, typically the electrons are actually shared between these atoms. And so they're referred to as molecules because they act differently. And we don't need to think about electrically neutral anymore. Instead, now, what we want to focus in on is how many of each of the atoms there are. And we make use of a series of prefixes here. So we're going to do, we're going to use prefix 1 plus the name of the first nonmetal, whichever one's listed. We'll learn reasons why one of the nonmetals is listed first, then versus the other later on, and then prefix 2 with the other nonmetal, and we'll actually change the ending on this one to IDE as well. All right, so let's look at what the prefixes are. We kind of need these to start off. And these are all going to be based off of Greek names. So these are the Greek prefixes. We have the prefix for 1, which is mono. 2 is di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. And 9 is nona. 10 is deca. And then if you want to keep going, you have to use a different prefix in front of that. It would be undeca. And you kind of keep going from there. So I think I have these written. And that's Latin for 1, undeca. So we use a combination of Greek and Latin. All right, so let's go ahead and try to name a couple compounds. Let's start with some simple ones. We have carbon, and this first prefix sometimes is optional depending on if it's got a mono 1 prefix. So let's take a look at that. So I talked about this one in lesson, I think it was the last lesson, carbon monoxide. Okay, so CO. All right, so in this one we have carbon and we have oxygen, and we have one of each of them. So you might think about naming this as monocarbon monoxide. There's a couple of weird things on this one. Typically we don't list the prefix for the first nonmetal if it's got a prefix of 1. Okay, so that's one thing. The second is if we have oxygen, and there's like a prefix that ends in a vowel, we'll sometimes leave out one of those vowels if it's the same letter. Okay, so we could call this carbon monoxide, and that'd be fine as well too. All right, but now if we change the number of oxygens here, we've changed the molecule, and it becomes carbon dioxide now, right? And so we have to keep both of those vowels because they're different vowels. We can keep doing these for the nitrogen compounds. We typically work with talk about a lot of gases here because the simplest molecules are gases. So here I have NO, and this is given the systematic name of nitrogen monoxide. But it also has a common name, and this one is known as nitric oxide, or laughing gas. Some other common names will come up when we're learning this. So we have, what about NO2? So NO2 is nitrogen dioxide. N2O is another one. So here, this one is dinitrogen monoxide. But this one is one that has a common name, and it's typically given nitrous oxide. Okay. We can also have something like N2O3, which would have the name dinitrogen. Oops, I keep writing a T there. I don't know why. Dinitrogen trioxide. See, this is kind of fun. So you can learn how to name compounds really quickly if you just practice a little bit. There's another website. It's really good for learning how to name compounds. It's just ptable.com, and you can go and look at compounds here, and then you can kind of play around. You can click, you can drag these in here and say nitrogen, oxygen compounds, and you can look and find the names for them. So nitrogen dioxide, NO2, N2O, see it has nitrous oxide listed, the common name. So that if we click though, we'll see, oh, I got it mixed up. Nitrous oxide is laughing gas. Sorry about that. You'll see the systematic name listed here as well. So dinitrogen monoxide. All right. Don't get it confused with nitric oxide. That's a colorless gas. We don't want to probably use that one there. That's a completely different compound. All right, so that's a really great place to kind of look and learn how to name compounds. And then what other ones did I want to bring up? Okay, a couple other things. Some other common names here. H2O. Okay, what's that one called? Think about it for a second. Did you say dihydrogen monoxide? Or did you say water? Okay, so you can say either one, right? Water has the chemical formula is H2O. I'm trying to look here. I think it says it on here. It should say properties of water. Yeah, dihydrogen monoxide. It's rarely used chemical name. So most of the time, most people don't use it. But this is actually a really fun website. Is it? I can't find it. Never mind. Getting sidetracked here. So this is water. And these are some other ones I want you to know. So water, and then NH3. This one we'll use a lot. This is called ammonia. Okay, so learn that. Ammonia, AMMONIA. And CH4, that's methane. Okay, so those are the ones I want you to know. Those are common names. All right, so now we've gotten basically to the end of our lesson. Let's practice a little bit. So I'm going to pull this up here. Okay, let's go here. Okay, cool. So pause the video and see if you can answer these questions within 5 minutes. Some of them might be a little bit tricky. Some of them are from problems from last lecture. And you might not know some of these yet, but I'll tell you this one, alkaline earth metals are in the second group. Okay, so go ahead and pause the video and see if you can answer these questions. Okay, did you answer those questions? Okay, if you did, good. I'll go through each of them. So number one is a neutral atom of gold 199 has how many protons, neutrons, and electrons? So if you should start by looking at your periodic table and finding where gold is. Gold is AU, so you need to know what the symbol is of gold, or you can find it here. So gold typically has 79 protons. Well, sorry, it always has 79 protons. So 79. How many neutrons does it have? Well, it's going to have 199 minus 179, or 100 neutrons. And if it's a neutral atom, it's going to have 79 electrons. Okay. Second question, which ion has 26 electrons? All right, well, we're going to need to look at our periodic table. And all of these have a positive charge. So if we start here with chromium. Chromium 2+ is going to have 2 less electrons, because if it loses a negative charge, it becomes positive. So chromium 2+ is going to have 22 electrons. All right, so then it's not chromium. Iron, neutral iron has 26, but 2+ iron would have 24. We got to go 2 more to the right, and we'll find nickel. And so nickel 2+ would be the one that we're looking for. Question 3. 2 isotopes of a hypothetical element exist with abundances of 30% of the 100 mass number isotope and 70% of the 101 mass number isotope. What's the approximate atomic mass of that element? Well, right off the bat, we know it has to be somewhere in between the atomic mass of 100 and 101. If you're paying really close attention, you would notice that the atomic mass is not the same as the atomic weight of that isotope, but it's fairly close. We can go back here and take a look. So let me show you. So if we had, like, for example, chlorine 35, its atomic mass is just slightly less for that isotope than what the atomic mass, the mass number is. So we'll just say that the mass number of this one's 100, and we can multiply it by the fractional abundance. So 30% is 0.3 as a fraction, times 100 gives us 30. And then we can take the other fractional abundance, multiplied by 101 this time. .7. We can add those together, and we would get that the approximate atomic mass of X is 100.7. The name of the particle that gives particles mass is a kind of a tricky question, because you might have thought that it's the protons and the neutrons and the electrons, because they all give particles mass. But this is a kind of a tricky question. Name of the particle that gives other particles mass is really what I should say. And in this one, I'm looking for the Higgs boson. So that's a particle that I talked about in lesson 3 that gives other particles mass. But if you said the proton and the neutron and the electron, that's fine too. All right. Question 5, the alkaline earth metals. So again, we didn't really cover this yet, so don't be frustrated. I'm trying to introduce a lot of new things to you at once. But the alkaline earth metals, if we look here at our periodic table, we see that's this one here. And you might have noticed a trend already, but that we can also look at this periodic chart, and we'll see that all of these form +2 ions. These are fixed charge ions. The correct name for N2O5, well, we need to know what our prefixes are and which, and that we are using this set of rules because we have nitrogen and oxygen, which are both nonmetals. So N2 is dinitrogen, and then 5 is penta, so it's dinitrogen pentoxide. So I guess we're going to get rid of the A just because it sounds weird, pentoxide. So again, it's kind of unclear when you're supposed to get rid of that vowel or not. But don't worry about that too much. And then these other symbols here, this is a Roman numeral for 2 and Roman numeral for 5. We'll get to that later on. Those are for variable charge metals. And then this last one is asking about a particle diagram for which of these could represent a heterogeneous mixture. Well, in the first one, A, I have 5 black spheres, and this looks like it's the same element floating around. It could be an ideal gas. In B, I have a molecule made up of a black and a white sphere. But it doesn't look to be a mixture to me. A mixture is 2 different compounds. C, 2 different compounds, heterogeneous mixtures is 2 different compounds that can be visually distinguished or have 2 different phases. So then that leaves us with C and D. Well, D has 2 different compounds. A compound and an element appears. But that mixture looks to be evenly distributed. We wouldn't be able to see the individual atoms probably, but they both appear to be gases, the way they're kind of moving around that chamber. And then C looks to be like either a liquid or a solid down here, and then a gas. So this one here is representing this heterogeneous mixture. All right, well, I hope you learned a lot this week, and there's 2 homework assignments for you to work on to kind of learn this material more. If you have any questions, feel free to reach out. I look forward to any feedback that you have as well. Take care, and I'll talk to you next week.